write the inverse of a relation that's been given as an equation? Well, recall that when we take the inverse of a relation, we want to swap the x and y coordinates of each pair. And the key thing to keep in mind here is that it's not the labels that we care about. It's not the label x and the label y. It's the pairs of numbers that we care about. We want to swap the order of the pairs of numbers. So how can we make that happen? Well, here we have a relation R consisting of all the pairs x, y, such that the first number, x, we square that, and then we subtract the square of the second number, y. And the result is 9. If the result is 9, that pair is in the relation. To get the inverse relation, we want to be somehow taking the second number squared minus the first number squared. And there are two ways that we can accomplish that. The first way is to swap the order of the symbols x and y in the sample element. So we'll still have the set of pairs where x squared minus y squared is 9. But now we'll say that they're the pairs y, comma, x. So notice this is now the second element, the second entry in each pair. And this is the first. So we accomplished what we wanted. The other way we can do this is to swap the x and y in the equation. So we'll leave our sample element as xy, but then instead of x squared minus y squared, we'll write y squared minus x squared. And so again, this is the second element, and this is the first. Notice if we swapped both, then we would still have first squared minus second squared. That would just be r again. So we have to choose one or the other. And technically speaking, we can choose whichever option is most convenient for whatever we want to do next. But in practice, our real goal here is to work with functions, where we're thinking of x as representing the input and y as representing the output. And it makes more sense to keep xy as the form of the pair. So it makes more sense to keep the pair in the order xy and reverse the x and y in the equation. So that's what we'll usually do, unless we have a super compelling reason to do something else. And of course, keeping in mind that our goal is to work with functions, sometimes after we swap x and y in the equation, it will be useful to solve the equation for y. Here we have the relation S. S is the set of all pairs x, y, where y equals 2x minus 6. Now, this is a function. We can tell because the equation is in the form y equals stuff with an x in it. When we write the inverse, so we keep the sample element xy, but then we swap x and y in the equation, it is not obvious whether or not the inverse is also a function. To make it more obvious, we can take that equation and solve it for y. So I'm going to write 2y minus 6 equals x, just to have the y on the left. We'll add 6 to both sides, so 2y is x plus 6. We'll divide both sides by 2. Y equals x plus 6 all over 2. Then we'll distribute the 2 to each term, and we get y equals a half x plus 6 divided by 2 is 3. Okay, we could solve that for y. So the equations x equals 2y minus 6 and y equals half x plus 3, those are equivalent equations. We know they're equivalent because we only used our basic solving moves here. So any pair x and y that's a solution to the first one is also a solution to the second one. So we can describe the same relation as the set of all pairs x, y, such that y is half x plus 3.